Hi, folks. This short talk is going to introduce the modeling component of the CO2 PIP project. And this is really the integration piece of the proxy integration project. We're trying to bring together all of these data coming from the samples, the work that the whole community has done to generate a better understanding and better quantitative reconstructions of Phanerozoic CO2. And this is the challenge. If you go to Wikipedia today and ask it to show you the Phanerozoic history of CO2 concentrations in Earth's atmosphere, this is what you get. It's a mess. What do we know? What can we say with confidence? What can't we say? Where do we need more information? Our community has been innovative and creative over the years in generating myriad different approaches to estimating CO2 concentrations in the past. All of these are demonstrably imperfect. Each has its strengths and its weaknesses. Some are better understood than others. How do we combine all of the information from these different approaches to leverage it and generate the best quantitative understanding of past CO2 that we can? Moreover, we actually know a lot about the carbon cycle and how it works. And this understanding has been accumulated and integrated in numerical models of various different levels of complexity. Can we leverage this understanding and combine it formally with the proxy information to generate a record of past CO2 concentrations that's not agnostic to our understanding of the physical and chemical processes that control the system, but actually incorporates it? This is a major challenge, and it's a challenge that will require a community effort to overcome. Overcoming this challenge, however, may also require us to change the way that we think about our work as a community. In particular, our use of proxies to reconstruct CO2, how we actually go about this work and these calculations, stems from a very siloed disciplinary focus, which inevitably has grown out of proxy development work, where individual investigators are focusing on a particular system and trying to use it to reconstruct CO2 in the past. And this has given rise to what I'll call here backwards thinking about proxy reconstructions. This backwards thinking starts with a focus on the proxy itself, and then works backwards from that proxy using mathematical formulas, other ancillary data to reconstruct estimates of CO2 concentrations in the past. We may have two different proxy methods available to us to reconstruct values at some point in the geologic past. And we consider these as two independent estimates, giving us two independent measures of CO2 concentrations at that time. In general, we have different groups working on these different proxy systems. They make different assumptions and use different approaches to doing their calculations, to error propagation. And this leaves us with questions about the comparability of the values that we reconstruct. The reconstructed values themselves, we typically treat as two independent statistical estimates of the CO2 concentration at that point in time. However, they're almost never consistent. How do we combine these? They can't both be correct. In order to get around these challenges, we think we need to pivot our thinking about our proxies to a perspective that we would call a forwards thinking approach. Here we start not with the proxy that we happen to have measured, but with the environmental conditions we're actually interested in. For example, the CO2 concentration itself. And we recognize that at any given point in the past, if we're thinking about global average CO2 concentrations, there's actually only one true value for that quantity. And that quantity then influences and gives us the values that we observe in our proxies. The challenge to us is to describe the relationship between that quantity that we're actually interested in and the proxies. How does the value of CO2 give rise to the proxy values that we observe? And we can do this through the development of mathematical proxy system models that describe the links between the environmental conditions we're interested in and the proxy values we observe. Proxy system models can be simple or complex. They can be very mechanistic or highly parameterized. But regardless, they give us an opportunity to leverage our understanding of proxy systems in many very productive ways. And they have major advantages over the traditional backwards approaches that we've taken in the past. Proxy system models let us harmonize our assumptions that we use inevitably when we're interpreting our proxy data. And this can give rise to more self-consistent calculations used in interpreting disparate proxy types. In developing our proxy system models, we can also recognize that although our traditional proxies are typically things that we can measure in the geologic record, which might be most strongly influenced by a certain environmental parameter like CO2. In fact, there are many other things we can measure in the record which might be influenced to a lesser degree, right? Or place constraints on the relationships between the environmental condition and the proxies. And we can measure and add into our proxy system model, when available, one or many different ancillary variables that help us to constrain one or more proxy interpretations. And perhaps most importantly, when we use proxy system models in a forward-thinking sense like this, we get a sound mathematical foundation for integrating information from multiple proxies. Rather than trying to back calculate two independent estimates of CO2 concentration and figure out how to combine those, we're now working forward and trying to find the CO2 concentrations which are most consistent with or best explain all of the proxy data that we have for that place and time. Numerical tools like Markov chain Monte Carlo sampling provide solutions to solving these problems and to finding the CO2 values, as well as all of the other proxy system model parameters, which best fit the data that we have available. And once we have robust proxy system models in hand, they're useful for large-scale integrative projects like CO2 PIP, but they also provide a new way, a complementary way, and hopefully useful way for individual investigators and groups to interpret their data. They become a community resource. Finally, proxy system forward models and MCMC inversion in a Bayesian context provide a natural way of integrating proxy data with carbon cycle models. As drawn here, we're tackling the traditional problem of trying to reconstruct a CO2 value at a given point in the geologic past. However, it's just as easy in these analyses, if a little bit more computationally intensive, to represent the environment not as a single value of CO2 at a single point in time, but as output from a simple or even complex carbon cycle model. And therefore, we can take the data whenever we have the proxy data and use it to help constrain and select the carbon cycle model scenarios that are consistent with those data. And we can do that across all of the data we have, ultimately giving rise to a new integrated model data constrained reconstruction of Phanerozoic CO2. Our project team is very excited to push this approach forward. However, this is a community effort and we need the community's involvement in two fundamental ways in order to make this possible. First, success is obviously and intimately dependent on the data that we have available. We'll be working with the community closely to try to get the best data possible. And to implement this forward-thinking approach, the type of data that we need is perhaps a little different than we've thought of in most of our synthesis efforts in the past. We're talking here about not just integrating interpreted estimates of CO2, but integrating our interpretation of all of the data themselves. And this means that we need raw data. We need the raw measures that the community has collected, not their interpretations of what those data mean in terms of past CO2. These data need to be as complete as possible. And so we'll be working with the community to try to fill in missing values or add data to data sets that should add value for individual researchers as well as improve our ability to integrate. And importantly, these data need to be collected and compiled in a consistent way to allow us to bring them into this mathematical analysis efficiently and effectively and without errors. In order to facilitate all of this, the Cenozoic CO2 Research Coordination Network members have already invested a huge amount of effort into developing spreadsheet templates that are designed to allow consistent and comprehensive reporting of the raw measurements that have been made for a wide range of different proxy systems. Getting everybody's data into these formats will be a lot of work, but the CO2 PIP team has personnel and resources that we are excited to dedicate to help all of you in this process. Second, we need your ideas, your expertise, your input as we work to develop these proxy system models. In order for these models to be as good as possible as useful as possible, and for the community to have confidence in them, they need to reflect our state-of-the-art understanding about these various different proxy systems. We also recognize that our understanding is incomplete and imperfect, and that there are differences of opinion and perspective on these proxy systems within the specialist communities. We want to know that. We want to dig into it, and for those issues to come out so that they can be integrated into the models, we need to know what we know with confidence, as well as what is still uncertain. The ultimate goal of the proxy system model work is to develop resources that are built by the community and for the community. We want to develop models and tools that are useful to a wide range of investigators for a long time to come. And to do that, we need community buy-in and community input so that we're certain that everyone's perspectives are reflected and that what's being developed is as useful as possible to you. Thank you for listening, and thank you for your engagement with the CO2 PIP project. There's an incredible amount that we can do, both within the context of this project and in the longer term as a community, to improve our understanding of past CO2 concentrations in the atmosphere. We really look forward to working with you on the modeling component of this project and are excited and hopeful that what's developed here will be of use to the community for many years to come.